Assalamu alaikum everyone. So we were in the last class. Basically, we were discussing the refining article 8.5, refining the sketch. So sometimes to make a more precise root locus, we try to refine the sketch. Some additional rules we introduced. Okay, so one of them is actually after plotting the root locus to figuring out which point is on the root locus of specific gain on knot. So to do that, so we are still stuck with the same refining the sketch. So a small bit of it is left, and this is actually plotting and calibrating the root locus. So plotting and calibrating the root locus. Okay, so let us see what does it mean. So basically, whenever we are plotting someone, some additional condition may be provided. Say somebody is saying that you have to have try to figure out the pole location for which you have 20% overshoot. So 20% overshoot pole location and corresponding gain K, for which actually you are obtaining 25% of percentage overshoot. So plotting the root locus is not enough now. So after plotting the root locus, then you have to search for the point. So that will give you 20% overshoot. So how can we start with solving problem like this? So 20% overshoot. So as we know that overshoot is actually related to percentage overshoot is related to our zeta value. So damping coefficient, okay. So damping coefficient zeta, damping ratio basically zeta. Then you have formula that we have derived in chapter 4 minus ln percentage overshoot divided by 100. Okay, so in the last year, one of the quiz, they needed to apply this formula of zeta, but they forgot to review the chapter 4. So as a result, they face difficulty in the quiz to figure out the zeta line. So minus ln percentage over should be 100 divided by square root of pi square plus ln square percentage overshoot by 100. So basically 0.2. And now if you plot the values, then you're going to get 0.4559. Okay, so and we know that if we draw the line here, so basically we can find out an angle here, theta. So the cos zeta equal to basically cos theta. So if you have any pole here or any zero, so you can easily find out what is the angle here, and correspondingly that corresponding zeta value of that particular point or any point in that line you can figure out. So what will be the angle theta then? The angle theta will be cos inverse zeta. So we already figured out the zeta. So cos inverse 0.4559 will give us approximately 62.877. So in the Microsoft whiteboard, it's difficult to go into fractions, so you can approximate to 63 degrees. Okay, so let us try. Okay, so I actually haven't said about the system. The system we already used in the last class. The system was K, G of S, H of S, K, G of S, H of S. The one of the example that we already used, K S plus 3, so 1, 0. And the four that we have S plus 1, S plus 2, and S plus 4. Okay, so now they are saying that you have to figure out a point that will give you 20% overshoot. And that means along this angle 63, we have to check the points one by one, for which point actually the summation of the pole angles minus the zero angles minus the pole angles becomes odd multiple of 180 degrees. So for any point, if we can see that the summation of all the zeros angle minus pole angles is giving us odd multiple of 180 degree, then that corresponding point may be on the root locus. Okay, so for doing that, we have to draw the root locus first. We already have seen how to draw it in the last class. So say this is our arbitrarily the axis. Now we have okay, so we have one pole here at 0, at -1, at -2, then at -3 we have a 0, then we have another pole here. So what they're asking is to draw us an angle of 60, draw us an angle of 63 degrees. Okay, so we have to draw an angle of 63 degrees. Okay, so something like this. Okay, so what we already know what is the portion of the root locus. The root locus is this segment, and the root locus is this segment, and the root locus is the rest of the negative. Okay, up to the infinity. So the direction here is this, and these two will be merging together. We figured out what was our minus 1.33 was our approximately our the centroid. So based on that, we have drawn 60 degrees and minus 60 degrees, something like this. So 60 degrees here, then minus 60 degrees or 300 degrees somewhere here. Okay, so then we had these two poles actually merging together. These two poles are merging together. Then we also calculated the breakaway point. So approximately 4 point something was the value. So 0.4 something like that. So basically vertically and at 90 degree they'll leave. Then gradually they will approach to the to our asymptotes. Okay, so something like this. Okay, now actually they are asking you to figure out this particular point here. Okay, so this particular point we have to figure out. Okay, so we have to figure out this particular point. So what the point corresponds to 20% overshoot. So this point we have to figure out. Okay, so how can we do that? So for that, what do we have to do? So say we are taking any length in this one. Say this is up to 2. So this is length. Say this length is approximately r equal to 2. So this length we are calling r. So we can put a constructed table, the table with different values of r, say r equal to different values and corresponding angle theta. So r equal to maybe 2, then we can increase or decrease, say 2.2, then we can say, if we say that the angle theta is not decreasing, then we can go for maybe 1.8, something like this. So we have to arbitrarily generate the table. So in the book, actually, they have used a MATLAB program to figure out. But to have more comprehensive idea of the root locus, actually, I am doing all the calculation here. Okay, so then 1.8, maybe 1.8. Okay, so gradually the values will be reduced in this particular case. Okay, so you have to go into trial and error to see what will be the values of the angle. So this one is actually giving minus 2 is minus 251 point something 5. Then 1.5 they calculated minus 230.4. So arbitrarily you have to see. So as you can see that at 2 you have higher values of angle, at 1.5 it is reducing. So basically you have to go for 1, then you have to check 0.5. So this is how you have to try. Eventually what we are going to see that there is a change here. So in between these two there should be some value. So if you further approximate, so you're going to see that 0.747. At this particular value, the angle will be approximately 180 degrees, minus 180 degrees. Okay, so let us just let me just show one example at 2 how to calculate the values. How actually it is becoming minus 251. So idea is very simple. So the radius is r. So the angle here is actually theta. So if you want to figure r value is 2, then you want to find out the base. The base is r cos theta. Okay. So cos theta we already know. Cos theta is zeta. So r is basically 2 and zeta is 0.45 approximately. So say it will be 0.9. Okay. So this is base. And what will be height? So the height will be r sine theta, and that is basically 2 into sine 63 degrees approximately, or 64.877. So if you apply that, so you're going to get approximately 1.786. So at r equal to 2, the point that we are finding, that corresponding base value and the height value we calculated. So at r equal to 2. Okay, so rest of the thing is as before. So basically you have to draw the line to measure the angle from each and every pole and 0 to that particular point. Okay, so this one and this one as well. So say this is your theta 1, this is your theta 2, this is your theta 3. Okay, then this is your theta 4, and this one is your theta, this one is your theta 5. So what is our formula? The formula is very simple. The formula is summation of the pole angles, the summation of the zero angles minus summation of the pole angles has to be equal to odd multiple of 180 degrees. So here only theta 2 will be positive, rest of them will be negative. So theta minus theta 1 plus theta 2 minus theta 3 minus theta 4 minus theta 5. So basically, minus theta 5 can be, we can use the 180 degree minus the angle, that formula for that. Okay, so this summation has to be equal to 180 degrees. So we have to check whether it is 180 degree or not. If it is 180 degree, then that particular point is on the root locus. But if it is not, then this point is not on the root locus. So height we already calculated. Height will be always remaining same, and the base will be changing. Okay, so the base itself is 0.9 approximately. Okay, so 0.9. So we can figure out what is tan inverse minus tan inverse. Height is always same, that is 1.786 divided by the base. This pole is actually at -4. So -4 minus 0.9. So basically it will be 3.1 magnitude. We're just taking the magnitude because we're taking care of the angle by their physical position. So plus tan inverse. So it will be, height is always same, 1.786 divided by, so this is at -3, so -3 minus 0.9, so basically 2.1. Then you have minus theta 3, that is tan inverse. This theta 3 is at -2, so it will be 1.786 divided by 1.1. Okay, so 2 minus basically 0.9. Similarly, the next one, tan inverse 1 minus 0.9, basically 1.786 divided by 0.1 minus, this time 180 degree minus, because we are taking the other angle. So 180 degree minus tan inverse. Since the pole is at origin, so it will be the height and the width of that particular point, height and the base of, so 1.786 divided by 0.9. Okay, so now just use the calculator to figure out all the points, and you'll find that the result is minus 251.4767. So definitely this is no way closer to 180 degree. So basically, as we are going to see that this point doesn't belong to your root locus. So this is what is called calibrating. So any point, if it is given, in this particular case, they have given a distance r, then from r you figure out where is the base and the height. So basically you have to figure out the location of the point, and from point, all the point you just draw the line and figure out the angles, and if the summation of the zeros minus the summation of the poles become odd multiple of 180 degrees, only then your that particular point will be on the root locus. So this can easily be done using a MATLAB program, and in the book actually they have done that, but for better understanding I actually calculated the whole thing and then figure out. So and similarly, if in this particular case, as we already said, that at a value, because in the example it is very difficult to do repeated calculations. So at 747 basically, r equal to 747, we'll approximately have the theta equal to minus 180 degrees. So this is on the root locus. And then what you have to do, you have to find out the value of the k or gain for which this is happening. So how can we find it out? The product of the pole lengths divided by the product of the zero lengths. Okay, so this will simply, because we already know the height, we already know the base value. So just apply the Pythagoras for each point, and eventually you can easily figure out for what value of gain we are actually we have that particular point on the root locus. And in this particular case, if you do the calculation, you're going to see that the gain value is 1.71. So whenever the gain value is 1.71, okay, then r equal to 0.747 will be on the root locus. So this topic was left, I forgot to discuss. Actually, the time was not that there as well. So plotting and calibrating root locus, this is how you have to figure out whether any point is on the root locus or not. So then we have example 8.7, article 8.6 is basically an example. The title of the article 8.6 is an example. So they actually summarize all the rules that we have studied in article 8.4, general formulas, then additional formulas in 8.5. Then they want to apply all of these into one particular example. So that example is your example 8.7. Example 8.7. Okay, so let us apply all the rules that we have learned into this particular case. So 8.7, again, the unity feedback system was there. So at least sometime let me draw the diagram. Otherwise, you always I am always writing the function kg of s h of s. Then you may be confused in the example by looking at the diagram. So k s square minus 4s plus 20. Then you have s plus 2. Then you have s plus 4. Okay, so unity feedback system. So I was actually interested about taking the quiz on the chapter 8 because this is a more important chapter. Steady state error is also important, but it is more compared to, because this is design and analysis. Base of this one is actually will help you to proceed with the chapter 9. Chapter 9 is designing via the root locus. So whatever we are learning here, that will actually help us to design in the chapter 9. And I think it is the biggest chapter as well. So a lot of things they actually covered there. But you intend to go with the chapter 7. So let's see how the quiz goes, because I was actually willing to see how the thing actually goes there. So now in this example 8.7, again they have used the MATLAB, but we don't want to do that, because in the exam hall, maybe this time, if it is an online exam, you can have MATLAB, but in general, we don't have the MATLAB in the exam hall. So first point that we should figure out is the location of the pole and the zero. Pole is very easily locatable. So the poles that we have, 1, 2 is basically at -2 and -4. Now the zeros we have to figure out. So zeros is minus b plus minus b squared, that is 4 square minus 4 into 20, so divided by 2. So if you do a bit of calculation, you're going to see that it will be -2 plus minus j4. Okay, so basically we have two finite zeros and two finite poles. The zeros are at complex zone. Sorry, it is actually plus, because we have a plus sign here as well. So, and the zeros are at in the right half plane. So what they're asking us to find is, first of all, they're asking us to find out the exact point point and gain. So when it crosses 0.45, so this is your damping ratio line, 0.45 damping ratio line. Okay, so this is one. Number two, they are asking you to exact point and gain. So exact point and gain, same thing. Whenever it is crossing the j omega axis, axis crossing. And third, they're asking you to find out the breakaway point. So breakaway point. And finally, so basically they're asking is the range of k. So range of k for stability of the system. So as the range of f for which the system remains stable. So this is what they are asking, but they use a MATLAB. That is why their order of the question is not actually. I don't think the order is perfect because of the fact that whenever you are plotting the root locus, by default you have to apply this formula. And whenever then for refining the root locus, you have to apply this one. And then automatically you can find out what will be the value of the gain. Then it should be the fourth question. So what should be the zeta line after plotting it? So it should be, according to me, the fourth question. So let us try to plot the root locus first. Then we'll one by one going to answer the questions. So say we have try to plot it. So okay, so let us draw the real and imaginary axis. Okay, so at times it takes to use the ruler, but to have a better picture, it's better to go with that one. Okay. Okay, now, so plot the zeros and the poles. The pole is at 2. So we have a pole here, -2. And we have a pole here at -4. Okay, so at -2 plus J4, so sorry, +2 plus J4, we have a 0 here, and we have a 0 here. So for how many branches we will have? Because we have finite number of pole zeros are equal, so there should be 2 branch only. And then will there be any infinite lines? Definitely there will not be any infinite lines because the number of the infinite line formula is actually number of finite poles minus number of finite zeros. Basically, if they have their partner there, then they will not go for that one. So now this is, we know that actually they will merge together, the poles will be merged together to the breakaway point, and then they will go to the imaginary towards the imaginary axis to find their soulmate in those two zero location. So to refine the diagram, basically the next step should be is we should go for the breakaway point. So one of the transition method that we have used for the breakaway point was in the last class, that summation of 1 by sigma plus ji, the zeros, equal to summation of 1 by sigma plus pi. So let's see whether for imaginary axis, if we try to apply this formula, whether it gives the correct value or not. You can always go for that condition, that is dk by d sigma, but we want to see whether this formula works here or not. Okay, so we have two zeros. So one is 1 sigma minus 2 plus j4. Then we have plus 1 by sigma minus 2 minus j4. It should be equal to summation of 1 by sigma plus 2 plus 1 by sigma plus 4. Okay, so if you try to simplify, just multiply, cross multiply, simplify, and then we have to cross multiply. So if you multiply these two, it is actually going to be the formula, the roots that we already had. So, but instead of s, it will be basically, instead of s, it will be sigma. So basically, sigma square minus 4 sigma plus 20. Similarly here as well, so if you multiply these two, then it will be sigma square minus plus 6. So both of them looking together alike. Okay, so I have to be a bit careful about it. So 6 sigma plus 8. Okay, now if you add these two in the numerator, so basically this portion will be cancelled. So what we are going to get is 2 sigma minus 4. And here you will have 2 sigma plus 6. Okay, so just cross multiply and simplify. Then what we are going to get is 10 sigma square minus 24 sigma minus 152 equal to 0. Okay, so try to solve for sigma 1, 2, and this will actually eventually give us minus 24, so 24 plus minus, okay, so 24 whole square minus 4 into 10 into minus 152 divided by 2 into 10. So if you use the calculator, where you're going to get is two values you're going to get. One is plus 5.2774, and the other value that you're going to get is minus 2.877. Okay, so the plus value we cannot take because of the fact that only this portion is on root locus. Okay, so and the value is in between minus 2 to minus 4. So basically we have to take this value. This value is we cannot take. Okay, so this is our break. This is our break away point, that is approximately here, somewhere here. So minus 2.88 maybe. Now next thing is to figure out the j omega axis crossing. So for j omega axis crossing, we have to figure out the closed loop transfer function, and the closed loop transfer kg of s h of s is already there. So k divided k into s square minus 4s plus 20 divided by s square plus 6s plus 8. So this is kg of s 1 plus, same thing will be repeated because h of s is 1, unity feedback. So k s square minus 4s plus 20, s square plus 6s plus 8. So if we try to simplify this one, so what we are going to get is k s square minus 4s plus 20. And now here you have s square plus 6s plus 8 plus k s square minus 4s plus 20. So s square 1 plus k, then you have plus 6 minus 4ks plus 8 plus 20k. Fairly simple. So actually you are not bothered about the numerator, so I forget to write it. So this is our second order system, simple case. So s square s to the power n s to the power 0. Actually most of the is the most simplest case, I think. So the 1 plus k, 6 minus 4k, then you have 8 plus 20k. Okay, so 0 here, so automatically this one will be coming here. So 8 plus 20k. So basically what we have to do, we have to make this one 0, this row 0, to have all the rows 0 for figuring out geometry axis. So basically 6 minus 4k will be 0, k will be 6 by 4. So approximately 1.5 is the value of the k when it is actually crossing the geometry axis. So okay, now so this is the case. Now your value of k is 1.5, so basically 2.5 s square plus s8 plus 20 into 1.5. I think it is 30. Okay, so 30 plus 8, so 38. So s square equal to basically minus 38 by 2.5. So basically it will be approximately, because of the negative sign, if you take the square root, then it will be j plus minus, according to my calculation, 3.899. Okay, so we figured out j omega axis crossing. This is one of the answers. Okay, I think the second one they asked, and also for which value of k. So for k equal to 1.5. So basically, now we figured out approximately somewhere here we have the geometric axis crossing, somewhere here and somewhere here, 3.99 plus minus j 3.99. So also we figured out what is the breakaway point. So basically we can now try to plot it. It's difficult, as you know, so but please, this is how you to draw. Good thing is in real life you don't have to do this kind of drawing because of the fact that you can always apply the MATLAB for that. Okay, so you can always use a software for that. So something like this. Okay, so similarly, you will have symmetrical about the real axis. So somewhere like that. I'm not sure whether it is absolutely symmetrical or not. Okay, so then we have to figure out the point for which in this axis the point which through which if it goes, then it will maintain a 0.45 constant zeta line. Actually, it is also related to the percentage overshoot that we have seen in the last example. So 20% percentage overshoot. Okay, so that line. So we already calculated that for the last one, that is uh, theta is equal to approximately 62.8 something, or basically 63. So we have to draw a line of that. Then from the graph, basically from the graph, we have to physically figure out that point. Okay, so this is approximately 63 degrees, and if we use the ruler, then we are going to see that that will be going somewhere through this line. So this is not actually, since it is identical, it will be one point will be on the top side somewhere here. Okay, so it depends on how precise your drawing is. Similarly, that as you can see, my one is not that precise. You can also use a compass for this. So another one will be somewhere here. Okay. So basically, you can draw another line, and that should go through this one. And this zone actually is zone of value of zeta. Okay, so so this line is zeta line is 0.45. So as you know, cos theta, value of cos theta is increasing. So if you move in this way, the value of the zeta will be more than 0.45. And if you go this way, then the value of zeta will be less than 0.45. Okay, so this is how you can define the zone. Okay, so graphically, you actually have to figure out that corresponding point. So you can figure out what values of this value, approximately 3j. So j3, according to my drawing, which may not be perfect. So, and this is where approximately one, it seems minus 1.5, something like this. So you can find out the point. Then how to find out the corresponding gain k? K gain is simple again. So pole lengths, product of the pole lengths divided by the product of the zero lengths. Zero length. So what you have to do? You have to draw a line. I think I should use more color whenever this is available. So you have to draw a line like this from this one. Okay. Okay, so from each point you have to actually find out the lengths, corresponding length. Okay. Sorry about that. Okay, so then also from the downwards. So that is why it's better to use a ruler today. Okay, approximately here. So whatever the point that you have figured out, so all the lengths you have to calculate, and then you have to find out for which value of k. So it is physically possible without applying the MATLAB as well. So that is the intention. That is why I am actually doing in pen and paper, so that the depth knowledge that you need to understand the control system and the pole location and how to figure out all this calculation. In the last year, we don't have much time. Okay, so that is why I couldn't draw all this in the class. And since we are going online and we are having the flexibility of taking additional classes, so that is why I'm going much slower this time, and as well as drawing everything so that it become helpful for you. So I think we already figured out all the 4 questions they ask exactly. The last one. So last one is the value of k for which it is stable. So as we can see here, the value of k will be, starting value of k here is 0, And here we already, while we calculate the j omega axis, so we calculated the value of k equal to 1.5. So the range of stable range of k is basically k lesser than 1.5 is the range of k for which your system is going to be stable. Okay, so now article, this is example 8.7 and article 8.6 is done. Now the article 8.7, they are saying that we are good that we have assumed that we have only few number of poles, but it's, in some cases it may happen that we may have more number of poles than zeros, and in that case how to actually approximate second order system. So we have a higher order system, but we want to approximate second order system. So question will be why we want to approximate second order system. Okay, so the answer to this is basically our formulas that we have introduced in chapter 4. All the formulas are actually based on second order system. Okay, so if you want to apply the formula, then we have to somehow approximate our system as a second order system. Only then we can apply those formulas. Otherwise, we have to rely on the program software like MATLAB or Python to generate the root locus, and based on that, we can actually figure out from the simulation. But in the exam hall, as we say, that this time maybe you will have the advantage of the MATLAB, but in general, we don't have it. So we have to calculate by hand. So that is why we want to approximate the second order formula. So what are the approximations? Number one is we are assuming that higher order poles are far away, we should say, far away from dominant second order pole. Second order pole. Okay, so this is number one. Number two is higher order zeros will be cancelled by higher order poles. So higher order zero maybe close to dominant second order pole. Dominant second order pole is cancelled by higher order poles. Okay, so this is assumption number 2, and the assumption number 3 is if it is actually continuation of the 2, if not cancelled, then somehow we have to assume that higher order zeros are also far away. Zeros are far away. Okay, let us try to understand these with diagrams. So what does it say is say we have a 3-pole 1-0 system that we already discussed. Okay. So we have pole here, we have a pole here, and we have another pole here. Okay, so whenever your root locus, we know that there is three pole, so there is no zero. So our root locus will be something like this. They'll be merging together, and then they will have a 60-degree angle. There will be one will be going here, one will be going, and the other will be going here. So what it says that these are actually dominant second order poles, and they are actually determining the transient behavior. And this one is actually higher order pole, maybe third order pole. Okay, so maybe fourth, fifth, even higher order is possible. So what they are approximating is this higher order pole. Higher order pole is far away from these two dominant poles. Okay, so say in the next instance, they are here, and this is here. So basically, this is even better approximation. Okay, so and ideally, academically, or in this particular book, they have used 5 times away. So 5 times away, if it is, if the higher order pole is 5 times away from and the dominant second order pole, then we can approximate that the behavior of the system will be approximately closer to the second order system. Okay, so this is your rule number, the approximation number 1. And the second approximation, what they're saying is the second approximation is saying that okay, so the second approximation is saying that if you have something like this, okay, so one pole here, maybe one pole here, then you have a 0 here. So this is higher order 0, and we also have a pole here. Okay, so if the we know that the root locus will be this segment, and the root locus will be this segment. And as our k value increases, we are actually approaching here, here, then sorry, it will be, how many infinite lights should be there? There should be 2 infinite light, isn't it? And whenever it is 2, actually it will be going straight up and straight down. Okay. So these are the dominant poles, second order poles. Okay. Now, this higher order 0, if this pole is more and more closer to this one, whenever it is here, say they are here and here. So whenever this becomes here, they are actually here and here. Okay, so the approximation says that the more closer the pole to the 0, so they can cancel each other approximately. And the behavior is completely dominated by this second order pole. So this is your second order, second approximation, that zeros will be cancelled by the nearby poles. And if they are saying that if it is not possible to cancel, in that case, somehow you have to approximate that this 0 is actually far away, like 5 times away. So even if it is also valid as an approximation, if it is possible to take it to that location. But if it is not possible, in that case, because we have to go into the exams, we have to use those second order formulas, but those second order formulas cannot be appropriate or cannot give the actual cases. So in that case, in the exam, if you see that these approximations are not true, then we have to, in the exam hall, you'll say that we have to apply the simulation, MATLAB simulation to validate the result. You are going to apply the second order rules, but you are not going to, you have to say that you are not certain about the behavior of the system. So you really have to apply the simulation to see how much it is varied from our calculated values. Okay, so and if it is in your practical life, then you always actually have to, whenever you're designing some system, after designing it, you always have to go for the simulation to validate your result. Is it okay? So this is always true, because like you want to design aeroplane or aircraft. So you are not going to actually rely on your calculation, and you make it, and then you see that some of the design was not good. So you cannot take a risk of that high uh, expense. So that is why in real life, you always have to make a simplified design first, and based on that, you design the control system. Then you have to always go for the simulation before you can actually implement the idea. Okay, so this is the approximations, and related to that, actually, we have one example, example 8.8. So unfortunately, because of shortage of time, they also use the program for this one. So I cannot finish it doing manually. So maybe in the next class, I'll try to do it, okay, and see how to figure out this one. So this task is left, or maybe I'll just give you the handout in the Google Classroom so that you can look at how to do the calculations. Now, Article 8.8, this is simple. And as we said in one of the class, that not necessarily that it always has to be the gain K for which we have to plot the root locus. So it can be any parameter. So this is your Article 8.8 is saying that thing. So generalized root locus. Generalized. Okay, so LI, generalized root locus. So now, if it is a generalized case, then how we are going to plot it? So say we have a transfer function like this. So this is 10 divided by s plus 2, s plus 2 into s plus p1, say. Okay, so then you have unity feedback again. CS, this is RS. Okay. So now they are asking is instead of K, say our parameter that we are interested to change is P1. So we want to see if the value of the P1 is changed from 0 to infinity, then how the system is going to behave. So how can we do that? So it seems very complicated, but actually it is very, very simple. So based on the system that is being given, you first thing you have to do is you have to find out the transfer function, closed loop transfer function of the system. Then from that one, you have to find out the function kg of s, h of s. Eventually, this is the format that we have to look. So if I figure out the closed loop transfer function, so 10 divided by s plus 2 s plus p1 divided by 1 plus kg of s h of s. So 10 s plus 2 s plus p1. Okay, so if you simplify, then 10 divided by s plus 2 into s plus p1 plus 10. Okay, so what it is going to be look like is 10 divided by s square plus twice s, then you can just take common of the p1, you just multiply with s plus 2, because the whole idea is to separate the contents of p1. So whatever the parameter is multiplied with the p1, those has to be isolated from non-p1 terms. So what we have is 10 divided by s square plus twice s. plus 10 plus P1 into S plus 2. So P1, non-P1 terms has to be isolated. Then P1, this parameter has to be divided by non-P1 terms. So what you are going to get here is, or actually both the numerator and the denominator, you divide by this term. So what it is going to be 10 divided by S square plus 2S plus 10 divided by 1 plus P1 S P1 sorry, P1 S plus 2, then S square plus twice S plus 10. So now this is your function K G of S H of S. Okay, so whatever the parameter given, you have to bring it in a format like this: 1 plus that parameter into some function. So now if you plot your transfer function, the root locus, then it will be your, so this time K G of S H of S, K is actually here P1, so P1 S plus 2, then S square plus twice S plus 10. Okay, so pole 0 you can easily figure out. The pole location S1, 2 will be eventually, if you say minus 2 plus minus 4 minus 4 into 10, 36. So divided by 2, so minus 36 is minus plus minus J6. So minus 2 plus minus J6 by 2 is basically minus 1 plus minus J3. So if we try to plot this one, what it is going to become is something like this. Okay, so minus 1 plus, okay, make it a bit larger. So here, sorry, you have a pole here and you have a pole here, and you have a 0 here at minus 2. So how many infinite lines should be there? Only one infinite line, and one infinite line will be at okay, so you also have to figure out the break here, break. In this case, actually, there will be only, because the poles. Okay, so which segment is on the root locus? Definitely, this segment is, only this segment is on the root locus. Okay, so this segment is on the root locus. And since this is a 0, so a pole will be coming from here. Okay, so somewhere here you have to, so how it will look like. So one of the pole will be actually, one of the pole here will be actually coming, both of them will be, because they're identical, so both of them will be coming something like this. Then one of them will be coming here, and another one will be coming here, because somewhere there you have at infinity you should have another 0. Okay. So I'm just approximately drawing it, but whenever you're drawing it, you have to figure out what is your breaking point. Using the calculation that I have shown, as well as, okay, so this is how, now here your value of P1 is actually 0. Sorry, the value of P1 is infinity here, and here the value of P1 is actually 0. So the root locus started from this location, and one of them ends here, the other one here ends here. Okay, so this is the generalized root locus, and for the generalized root locus, what you have to do, you have to find out the transfer function and find out the format, like whatever the parameter you have, 1 plus that parameter into some function, so that will give you a kg of s, h of s, and based on that one, you have to plot the root locus. Actually, once two small topics are left in this chapter, but I think time is almost up. So let me stop here today and see you in the next class.